All right. I want to talk again on uncertainty and the slit experiment. Um, I watched a video where the person was talking about instead of doing like a two slit experiment, I've seen this experiment basically done multiple ways where either you have two slits, right, or you just put like a thin line in between the beam and like split the beam, or um, you have one slit, but you squeeze it until it's like closing off most of the beam. Like if you're doing this with a laser. So what happens is as you pinch it, this video was talking about this where they pinch this slit so it's really close. As you condense the distance, right? What's happening here is that the beam, like that you're observing on the other end, on the other side of the slit, is being stretched out, is being pulled, kind of, and it's like lengthening. And we see this as, an increase in an increase in an uncertainty in um, where the particles of light are going to land, and we get this sort of wave distribution, and we call it an interference pattern, but I don't think that that's right. Um, and so I was watching this, and basically what was being said was as you reduce the area that the light can travel through, right? As we restrict its like path of travel, we are increasing the amount of we are increasing uncertainty in the result. And because as we reduce this, we know its position better, and because we know its position better, we can't know its momentum or something along those lines. Like that's like the uncertainty principle. And I'm not so certain about the uncertainty of that. I think what's happening there is it has to do with gravitational lensing, and it sounds bizarre. Because why would gravitational lensing be taking such a strong effect, such a visible effect at such a small scale? Gravity's weak, right? Gravity's so weak. It's so weak. That's all I hear all the time. It's such a weak force. It's 40 times weaker than everything else. What are you talking about? Gravity is everywhere. It's everything, right? How could you say it's such a weak force when you observe it in everything you do, right? I don't know. So, but what I'm saying is that what's happening is as you're squeezing it, right? You have these slits are made of mass, right? These are physical objects. So as you're squeezing it, you're also you're decreasing the space in between these two walls, and as you do that, these walls are made of mass, right? These walls have mass, and so what happens is instead of these particles getting shot straight through, like when it was wider, they just go straight through. There's no gravitational effects really affecting them, right? But when you start bringing the walls closer, some of these particles might travel close enough to the wall to be affected by its gravitational field and get slightly bent, right? And then some might travel even closer and get even more bent. And so as you reduce the size of this slit and you make it smaller and smaller, the likelihood of particles getting bent by the gravity of the slits themselves is higher and higher. And so what happens is that the the light's the particle of light's trajectory is, instead of guaranteeing it's going to go straight, basically it's starting to get You know, if it's slightly this way, then it goes that way. If it's slightly closer, then it goes even farther, and we get a wider beam on the other side because of this gravitational effect, kind of like fanning out the possible trajectories of the particles. And so it's not like, and so it's increasing uncertainty because we're increasing the amount of area it can land, but it's not a necessary function of the system, that it uncertainty must increase because we know its location better. I don't think that makes sense. I don't think that it makes sense that uncertainty has to increase because certainty in one area is increasing. I don't think that tracks. But pretty much what I wanted to say there is that, you know, it's gravitational lensing. And so that's why in the observer effect in the two-slit experiment, once we start observing these particles, the wave function condenses and becomes almost looking like two slits. That's because we're hitting the photons with energy. And so if we measure it to see if it's going left or right, it gets hit with energy. This energy gives it enough, gives the photon or the particle traveling through enough energy to not be affected by the gravitational forces as much. And so it just flies straight through. But when you don't, it's not getting that boost that is increasing its energy, that is keeping their energies at relatively similar levels. It's being bent, right? There's the chance that a particle will be affected by this gravitational lens. And yeah. I put here that a way to test this would be to both vary the width of the gap and then measure the particle's position. Like you can vary the width of the gap, see what happens, right? Observe that effect, then start measuring it while, measuring which, I don't know what is used to measure like a particle in these experiments, but whatever is done, right? Do that. After you've gotten basically your base set and gotten like your expectation, then vary the width while measuring it and see if it varies. And then what you do after you've done that, then vary the measurement method, right? Try and measure it with different wavelengths or different sensors that use different methods, right? And see how that changes the results as well. Because in theory, if you hit it with different, if you're using, I don't know, some kind of infrared sensor to know the particle's position, then if you changed it to a sensor that can use, I don't know, microwaves or something, it should have an effect on the particle. It should have an effect on the result. And if it doesn't, then if it doesn't, then it proves that something funkier is going on, and that's besides the point for right now. And see how the diffraction pattern. See how the diffraction pattern is affected. You know, higher energy light should result in less spread, and lower energy light should result in more spread. You know, because higher energy provide more energy and therefore speed to the particle passing through the slits or through the slit, and it should decrease the gravitational lensing effect on the particle. And basically, if someone does that experiment, tell me your results, because I think uncertainty is always there. I'm not saying that uncertainty doesn't exist, because it's not that things can't be certain. It's just that we can't be certain of everything affecting a system. We can't create a controlled system, a truly controlled system that reduces uncertainty, because we don't know we don't know what factors we need to control, right? So if we could control all possible factors, right, and we could predict with certainty where it's going to land, which I think eventually is possible. If we could do that, then that opens a door to a whole lot of other scenarios. And I'm just going to tack this on quick here because it has to do with uncertainty, is with entanglement and how that works. Because the thing with entanglement is that a particle that's entangled, it's in this like superposition or whatever, where it's both up and down at the same time. No, it's not in a superposition of up and down at the same time. It's either up or it's down, and it can be either of those two, and it can change between them. It can be, oh, I'm up today, tomorrow I'm going to be down, and that doesn't affect the system, because the other one is going to be the exact opposite in interactions, because they're entangled. So if this one's up, right, this one's going to be down. And so at any given point in time, they can change. They just change simultaneously together. And so when you measure it, you know this one's up and that one must be down then, because that's just how things are. But my question to you is, if does measuring interrupt entanglement? And if it doesn't, have you measured a particle that's been entangled as up down and then measured it an instant later and known that it's down up? Because I don't know, I have to do more research on entanglement and what's being done with it. But if measurement doesn't break entanglement, and the particle's orientation changes over time, then we need to figure out a way to confine its all we need to do is figure out a way to confine its orientation, set up some kind of environment or system where it promotes a single orientation for the particle, right? And then we can lock it in that state as an entangled particle, and then we figure out how to keep it in the opposite state, right? And then we have these chambers basically that hold these entangled particles, and when we want to send a message, we define down as 0 and up as 1, and then you have computer processing. And I don't know if that's what a quantum computer is supposed to do, but it would allow for instant communication across great distances, and I don't think it breaks anything. I don't think it breaks any laws to pass information like that, because no physical information is being passed, right? It's just our interpretation of the information that's being passed. If you look at a particle changing from up to down, down to up, is it passing any information to you? No. But could you then look at it and say, oh, it's saying hello? Yes. But that's your interpretation. And whether or not that's what's actually happening doesn't matter, right? So it's not breaking any laws of reality to be able to pass information that way faster than light can travel. And so I think that it is possible that that could be done eventually. And if we find that the particles have a cycle and they have to go back and forth, we can still work with that, right? So say the particle is up, and then after 0.00000 seconds, I don't know, I'll say 0.0, say in 1 picosecond, then it's going to go to down, then it comes back to up in like 3 picoseconds. If we can find a pattern, right, if we can find that oscillation pattern, then we can utilize that as well. And we know that at any given point in time, it should be either up or down, set on a standard clock, right? We say at exactly this time, with like a very precise clock, it should be up. And if you get a result of down, then it means this, right? Then a 0 was just transmitted. And if it's up at a given time when it should be down, then, you know, a 1 was, I don't know if I just said the same thing or not, but you get what I'm trying to say here, is that we can utilize that oscillation and compare what we would expect based off of a given clock to what we have. And then that can then be interpreted into the correct transmission. This is entirely speculative. I don't know if we can even actually isolate entangled particles like that. But if we can, and we can measure them and still keep them entangled, which I don't know if we can do that either, then I do see some potential there, which would be cool. I don't know if it would be crazy useful in the short term. Maybe it would be, but yeah. So that's what I've been. That's what I've got on my mind, I guess. I don't know. I was gonna say that. That's what I've been thinking. I don't know why. I don't know why I needed to say that. But anyway, peace out.